This call is now being recorded.
Okay, so we'll start this June 22, Unit 1. I will solve this entire paper again. And after this, you guys will have which homework papers as a homework. We finished, so this is June 22. In that case, the another paper that I will solve entirely is going to be your June 21. Okay, June 21 was, the June 21 paper was extremely tricky. So I'll solve that entirely in class. After that, maybe from next week, you guys will do some homework again, which is the October 22. In October 21, I don't think there was any exam. No, I'm not sure, but yeah, in October 21, I think there was no exam. So you guys will have to complete October 22, October 22 and October 2020, I think. Yeah, October 2020 also you guys have to complete. I'll give you the list, no problem. Now we'll quickly start with this one. Also for, I might be wrong at pronouncing your name, Janiru, right? Is it?
Yeah, teacher.
Okay. For Janiru, we're doing this June 22 Unit 1 paper. And for the classes, for the recordings of the paper you missed, I'll give you the recordings by this week, Monday or Tuesday, okay?
Okay, teacher. Thank you.
Okay, then for question 1, if we start 1 to 10 section A, whatever it is, the machine has a power of this much and transfers this much energy during a time of t seconds. Which of the following expression gives the time in t seconds? I mean, we just have to find out the time. This is what? Power, and this is your energy. We're basically using the equation power is equals to energy over time. Just rearrange it. It becomes energy divided by power. Energy was 150 and divide by 750. Yeah, 750, but energy was in kilojoules. You'll have to convert that into normal joules. So that becomes 10 power 3, 1000. So in that case, 150,000, 750. Option C is your correct answer, right? Quite easy to work. I just have to use the formula and then insert the values. Other than this, I didn't do anything else here. Okay, now if you quickly move on to your question 2. This time it says that a sphere falls through a viscous liquid as shown. This is a viscous liquid. Sphere is totally submerged inside the liquid. That means the volume of the displaced water is equals to the volume of the sphere itself, right? And which row of the table describes the upthrust, the viscous drag on the sphere as it is accelerating downward? If it's accelerating downward, that means obviously the downward force is greater than the upward force. In this situation, all the forces acting on it are weight, and the upward force is going to be drag and upthrust, right? This is the case. Since this is a viscous liquid, that means obviously drag is there. And they were saying that, what is happening to this viscous drag and upthrust as it moves downward. If it is moving downward, accelerating downward, that means obviously at this point weight is greater than drag and upthrust. But if you think about it in this way, for upthrust, the equation was what? Rho V, 1 minute, rho V, it was G, right? Yeah, rho V G. And for your drag, it was 6 pi r eta v term, but I cannot consider that in this way. Which of the table describes upthrust and viscous drag on the sphere as it moves, accelerates downward? Yeah, it's 6 pi r eta v term. In this case, obviously 6 pi r, these are constant values. Again, for this upthrust, if you consider, density of the liquid is constant, right? Wherever you go inside the liquid, density is same. And then again, volume over here, this one represents the volume of the water displaced by the sphere. As I can see in this case, the ball or the sphere is already inside the water, is only entirely submerged inside the water. That means the volume of the total displaced water is equal to the volume of the entire sphere. So volume cannot also change. And then for gravitational field strength, this is also constant. So everything in this example is constant. That means upthrust over here should be constant. Upthrust cannot change. Okay. So if upthrust cannot change, but we know at some point after traveling few meters inside the water body, the object would reach terminal velocity, right? In order to reach terminal velocity, this point accelerating downward, this is the equation. For accelerating downward, the equation is now weight greater than upthrust plus drag, right? But for your constant velocity, you will get, or v term, you will write this as weight equals to upthrust plus drag. Now, if you consider upthrust is constant, that means what over here must increase in order to make the right hand side balanced with the weight. You have to understand previously the combination of upthrust and drag was not big, was smaller than weight. If the combination of upthrust and drag was smaller than weight, upthrust is not changing, but somehow the right hand side is now equal to weight. So over here, which quantity must increase on the right hand side? Can anyone tell? Is my question clear for everyone? Imad, can you answer which quantity over here should change in order to make the right hand side equals to the left hand side?
Is it the upthrust?
No, upthrust is constant, right? Over here, density, liquid displaced volume, and your gravitational field strength, everything is constant at this point. If these three factors or these three quantities are not changing, upthrust cannot change, okay? So it doesn't matter wherever you are inside the water now, upthrust is constant, okay? So upthrust is constant, upthrust is not changing. And when would only the upthrust could change? Maybe when, like in some example where the ball was half displaced into the water, the ball was kind of, floating on the surface of the water. Then what happens? Half of the volume of the sphere is inside the water. So in this case, the volume of the water displaced is equals to half of the volume of the sphere. But in this position, from the initial start point of your question 2, I can see the ball was entirely inside the water. That means the total volume of the water displaced is already equals to the total volume of the sphere. Doesn't matter, the more you deep inside the water, it cannot displace more water, right? Because the entire sphere is inside the water body now. So the volume of the water displaced is equals to the total volume of the sphere. So volume also remains constant. So without any change in density, volume, and gravitational field strength, upthrust cannot change. So it doesn't matter if you're accelerating downward or accelerating upward. As long as your object is entirely submerged inside the water, your upthrust is constant. If upthrust is constant, then if I give you like random values, I think that will be easier to work with. Maybe at this point when it was accelerating downward, weight was like 50 Newton, upthrust was 20 Newton, and this is maybe like 10 Newton. Right after this, what happens? We can understand that now we have 50 greater than 30 Newton, right? 20 plus 10 gives you 30. But after this, upthrust will remain as 20. This will be 50. But in order to make the right hand side 50 now, what over here needs to increase? This this drag becomes 30 now itself, right? Previously, the drag was how much? Previously, the drag was only 10. Now, in order to make the right hand side equals to the weight, drag must increase from 10 to 30. So over here, what happens as your object is accelerating downward? Eventually, it will reach a terminal velocity where upthrust is constant, but the combination of the upthrust and drag must be equals to your weight. So in that case, upthrust is constant, drag must increase. Imad, is this clear now?
Yes, teacher.
So option B is your correct answer. Do not assign these values, by the way. These numbers I only assign for explanation. Is there any problem from question 2?
No, teacher. No, teacher.
Arif, from your side?
No question.
Okay. If we move on to this, which of the following is a scalar quantity? This is a vector, vector, and this is what? This is a scalar quantity. So obviously this one is your answer, right? Again, you can use dot multiplication where we represent mass as a scalar quantity, acceleration is vector, their product ends up getting minus. And for dot multiplication, we always consider the vector quantities as negative, right? Again, this one will be momentum is what? I think mass times velocity. Mass times velocity again have the same arrangement. That also ends up giving you the minus sign. And again, for velocity, it was what? Displacement over time. Displacement was minus divided by plus. Eventually, you end up getting a minus. Remember that for dot multiplication, we consider all the scalars as positive and vectors as negative, right? And after this, Work done is what? Force into displacement actually. This one represents distance moved in the direction of force. That is actually a distance with the direction. Eventually you end up getting a displacement. So force displacement, they were both vector, eventually giving you a plus sign. So over here, the only quantity that gives you a plus sign is your work done. So work done is your scalar quantity. I hope this is clear for everyone for question 3. Now if you move on to question 4, the graph shows relationship between tensile strength and tensile stress for a material, elastic limit and breaking point. Which of the following gives a Young modulus of the material? We know that Young modulus of the material can only be calculated for the linear section of the graph, right? So the area under the line from the breaking point, no, this doesn't give you the yield point. So this doesn't give you the Young modulus. This gives you the what? Work done, basically, right? This is tensile stress and strain. This is actually energy per unit volume or work done per unit volume. If you remember from the theoretical classes, area under stress strain graph always gives you energy or work done per unit volume. So this is work done per unit volume. Then again, area under the line up to the elastic limit, no, this doesn't actually specifically give you anything. Gradient of the tangent to the line at the origin, no. The stress divided by strain, oh wait, 1 minute. Stress divided by strain at the breaking point, no again. But this option C is your correct answer here, because they're saying that the gradient of the tangent to the line at the origin. At the origin, if you draw a line, right, this is how the tangent is going to be. Right, this tangent is also only calculating the gradient for the linear section of the graph. That's why option A is your correct answer. You know, Young modulus can only be calculated from the linear section of the graph. Linear section of stress against strain graph. Any question from this part?
No, miss.
No, teacher.
Okay, so we're done with question 4 also. Then we'll move on to question 5. A student determined a value of g by dropping a metal sphere from rest. Initial velocity is 0. The main motive was to calculate acceleration. The student measured the distance fallen, s was calculated, and the time taken, that means t is also there for the sphere to fall, right? This is, by the way, your unit 3 core practical 1. Okay. Then again, the student obtained a value for g of this much value. Which of the following could explain the difference between the student's value and the accepted value? We know the accepted value is 9.81 meters per second square, and the student's value came out to be 11.2, which is greater than the value that we're supposed to get. So they are saying that air resistance was not negligible. Even if the air resistance was not negligible, right? If you're taking air resistance as a part of your calculation, then the value for your A should be less, not more. Why it should be less? Because in these cases, what are the quantities you are measuring? S and T. I mean, the equation that I could use here is S equals to half, UT plus half AT square. From there, obviously, UT is going to be 0 because the value for U is 0. If you rearrange this equation, you kind of get the equation as 2SAT square plus 0. This is exactly in the format of y is equals to mx plus c, where we can understand that, if you draw a graph of 2s against t square, the graph will be a straight line passing through the origin, and the gradient will give you the value for your g or a. Now, in this case, if you are taking air resistance into your as a part of your calculation, that means now over here, time, you would need more time to travel the distance, right? You can understand that from this equation, if I rearrange it, it's going to be 2s over t over t square equals to a. That means if you're taking air resistance as a part of your calculation, time increases. That was supposed to decrease the value for your acceleration. Then the student's results were supposed to be less than 9.81. That's not what we got here. So obviously option A is not a correct answer. Then again, they're saying that the student's measured distance was greater than the actual distance. Like there must be some mismanagement happened by the student when she was taking a measurement for the distance covered. Again, now they're saying that this time 2s divided by t square equals to a. For a larger distance, yes, I'm supposed to get a larger acceleration, because you should understand, right? Distance and a are directly proportional, and a and t were inversely proportional. So by any chance, by any mistake, the student have did some miscalculation while measuring the distance, and maybe she used greater distance for the calculation than which the ball actually traveled. So for a larger distance, she got a larger acceleration. And over here, I did got a larger acceleration than my accepted value, right? So that's why option B is your correct answer. The sphere did not fall vertically. If it is not falling vertically, that would not modify my results. Okay, so this is not a correct answer. Again, the student measured time greater than the actual time taken. This is similar to your part A. Greater time gives you smaller acceleration, not larger acceleration. So option D is also not correct answer. 2s by t square equals to a. For a greater time, you're supposed to get smaller accelerations. Only option B is your correct answer. Is there any problem from this? What is this? Question 5.
No, teacher.
Arif, Imad, any problem? Any questions from anyone about question 5?
No.
Okay, then if we start with question 6. Also, I was actually saying, I am doing that, unit 3 class today for the Jan 25 batch, right after this class ends. So if you guys are free at 3 p.m. Bangladesh time, you guys can join that class. Okay, that's, just a free class. You guys can
Today.
join. Yeah, today, right after this class ends.
Is it compulsory?
Not for you. Not for you guys.
Well, actually, I only kind of sleep because I had morning classes today.
Okay, but it will be helpful for the question papers. For Arif, it's not necessary. For Janiru also, it's not necessary. But for Fayad, Imad, and Afti, if you guys could join the class, it will be helpful for your Jan exams also. Because you can see, Unit 3 is coming so often in Unit 1, so it's important if you guys could attend. Okay, then if you move on to your question 6, a rocket is accelerating horizontally due to a constant resultant force. The mass of the rocket decreases steadily as its fuel uses up. Which graph shows the acceleration of the rocket could change? Okay, over here, resultant force is constant, right? That means RF equals to MA. Force is constant, but problem is that mass is decreasing. In order to keep the force constant, acceleration must increase, right? Because every time, even for a smaller mass, it is accelerating with the same maybe 5 newtons per second, 5 newtons, right? If that is the case, then what happens? Obviously, the acceleration must increase to keep this resultant force constant. Another thing, even when the fuel didn't start burning up, the object was still accelerating, right? So that's why the graph over here is going to be option B, because it doesn't start from the origin. It will have some acceleration, and the acceleration will continue to increase as the mass continues to decrease, because mass and acceleration are inversely proportional, right? Is there any problem from this question 6?
No.
No, teacher.
Okay, then if we quickly move on to question 7, this is what parallel series arrangement for your wires, right? For your springs. Two arrangements, P and Q, of identical springs are subjected to the same tensile strength as force F as shown. Which one spring is subjected to a tensile, sorry. When one spring is subjected to a tensile force F, the elastic strain energy of the spring is E, and which row of the table gives the total elastic strain energy of each arrangement? Like for series and for parallel, you have to say. This is your series, and this is your parallel. One minute. Elastic strain energy for the spring is E. For the equation for elastic strain energy, what was the equation? Area under the graph of force extension graph was supposed to give you the elastic strain energy, right? So basically the equation was E equals to half F delta x, right? But then again, for your series and for your parallel connection, we had some equations built up. The equations were, for series, it was what? Total f causes 2 extension, right? And this time f gets divided equally for the two parallel connections. Just 1 minute, please. Sorry. Bolamo. Okay, sorry, as I was explaining that for series connections, there were some formulas, right? So we have to use the formulas. If you remember, for series connections, the basic formation was what? It was 1 minute. For series, this is your kx and this is again kx, right? K times extension, k times extension, they both extend at the same amount. And for your parallel connection, like over here for series, you are supposed to get the equation as, like k equals to k1 plus k2. And for parallel connection, you are supposed to get it as 1 over k, 1 over k1 plus 1 over k2, right? So if this is the case, I can break down what? Break down your force as kx. That means in this case, instead of f, I can write half, as we have this time we have a kx here and this time we have a kx here. For the total elastic strain energy for the springs, they're asking, yeah, total elastic strain for each arrangement. That means we have half k delta x, and then again this will be added with, so delta x square, and this will be added with half k delta x, sorry, 1 minute, x square. From there, what do we have? Half plus half eventually leaves you with 1 k x delta x square, right? So k delta x square. You have to remember that the value for your E was actually it was actually half k delta x square. And over here, I'm getting k delta x square. That means what? Over here, if I consider this as y, okay, the elastic strain energy for your series arrangement is y. If I consider that as a y, then we have k delta x square with 2 multiplied with e actually, right? For series connection, half k delta x square, and we had kx square. That means obviously 2 was multiplied with that half kx square. That's why you got 2 extension for your series connection. So for your series connection, I'm supposed to get 2e. And then again, for your parallel connection, if I write, I can see for parallel connection, the equation was the reciprocal, right? If the equation was for the reciprocal, then again, I'll consider the total elastic strain energy for the parallel connection was maybe Q. In that case, I'm supposed to get half. If this is K over 1 over K, 1 over K, then the equation is going to be a little bit different this time. Because this time we are going to use The equation was F equals to KE, but problem is this time we're using 1 over K and 1 over K, right? So yeah, there we're supposed to use 1 over, or only the x square over K, and then again half x square over K. Am I making any mistake? 1 minute. That is for your series connection, half K square eventually gives you the same value. Oh, this time there's a problem. Now the total force is actually given to each of the arrangement, right? Over here, the amount of force received by this first spring is actually F divided by 2. So eventually it will become K delta X divided by 2, right? So in that case over here, anyways, I was supposed to break down F as K delta X. This time I'll have to write this at K delta X square divided by 2. And then again, this will be added with half K delta X divided by 2, right? So you basically have 1 over 4 plus 1 over 4. That will leave you with half K delta X square, right? So you have to understand, 1 minute. This is 1 over 4 plus 1 over 4. 1 over 2 with 1 over 2. Yeah, I'm going to get half K X square. If this is, I'm getting as half K X square. Am I making any mistake? 1 minute. Yeah, it was K half Kx multiplied with X. So you get 1 by 4x and 1 by 4x. There were 2 wires here. Elastic strain energy is half Kx square by 2 and half Kx square by 2. No, this doesn't actually match with any of the solutions, because I can understand that for P it will be 2P and 2E, right? In that case, it could be either 2E for Q or half E for Q. If it's half E for Q, that means I'm supposed to get from my calculation as 1 over 4 K, K delta X whole square. So half force extension, I'm not getting either 2E or half E. Wait 1 minute. Let me just check the mark scheme for this. Okay, I actually forgot about the extension also here. I'll just explain this part again. In this case, obviously we're getting half of the force, right? For half of the force, I'm also getting half of the extension, right? Not like that, every wire are going to extend of the same amount like the previous one. In this case, if the extension was delta x, this time it will be also delta x by 2. Extension also gets divided by 2. So in that case, the equation for your Q is supposed to be half. For F, it was F divided by 2. For extension, this is also extension divided by 2, right? Extension is half, force is half, and this will be added with your half F by 2 and extension by 2. If I break down F now in terms of your Kx, so I'm going to get 1 divided by 8 K delta x square plus 1 by 8 K delta x square. So for this 1 by 8 and 1 by 8, I'm going to get 1 by 4 K delta x square. So if you remember, the original value for E was half multiplied with half K delta x square. The main reason for separating the half so that we can get this equation, half K delta x square, which was the value for your E. So we get half E for your parallel connection and 2E for your series connection. I should represent this as P. So in that case, option B is your correct answer. Is this clear for everyone?
Yes, ma'am.
Afti, Imad, Arif, Janiro, anyone, any problem?
Not a
Not
teacher.
it.
Okay, so we're done with 7. If we move on to 8 now, the velocity time graph shows the motion of a particle with constant acceleration at points P, Q, R and represents the magnitude of each area shown. Okay, this is outside the graph, we can understand, right? P is not inside the graph. And which of the following expression gives the total displacement of the particle? So for the total displacement of the particle, yes, Q is for this section, that's correct. And R is for this section, but since this is a vector quantity, R is positive and Q is negative, right? So it should be like, R minus Q. That's just it, R minus Q. P should never be associated with any of the equations because P was never a part of the graph. It was always R and Q related. R is in the positive axis, that's why R is positive. Q is in the negative axis, that's why Q is negative. So you just get R minus Q, right? Other than this, nothing. Then for your question 9, a cyclist rode along a slope with constant speed. That means force is 0, acceleration is 0. The increase in vertical height of the cyclist is delta H, and the slope was at an angle of theta to the horizontal as shown. Which of the so the forward force on the road on the bicycle was F, and air resistance was negligible. Which of the following gives the work done on the cyclist? If you consider drawing the particle here, so then we can easily distribute the forces acting on the particle or the cyclist. Weight was vertically downward, right? So if weight was vertically downward, this is your weight. And again, if this is theta, then this is also theta, right? So we have mg in the downward direction. Vertically downward, you have mg cos theta. Down the plane, you have mg sine theta. Reaction force above, and there was it was already stated that a forward force on the road on the bicycle was F newtons. That means over here in the forward direction you have a force of F newtons, and there was no air resistance, so no friction was there. So this is it actually. If you want to now find out the work done by the cyclist, for the work done of cyclist you have to consider using the equation. What work done is just what was the equation? 1 minute. Yeah, they're also saying that work done by the cyclist, but problem is we do not have the distance along the slope, right? How much distance was traveled by the cyclist, that is not given. If that was given, I could have easily used the equation force minus mg sine theta multiplied with the distance. Is given the fact that they have traveled, or they have given you the value for the distance traveled on the slope. If that is not given, then I cannot use this equation. Since they have only given you the vertical height, that means our force distributions are going to be a little bit different. Okay, since they have given you vertical height, I'm going to use the vertical component of the force that was acting over here. If this was force, there was no doubt in there that this was along the plane, this was the force. Then this time, we will have to work with the vertical component of the force also, vertical component or the horizontal component of the force. Right, this is how the forces are going to be. If this is F newtons, this is theta again. So this is going to be F, F sine theta. And then it's going to be F cos theta. So it maybe made a mistake. This is F cos theta. And this is your F sine theta. 1 minute, but work done by the cyclist, we only have force. And yeah, I know we are using the horizontal displacement again. Like we are using the easiest method because whatever the format I was going to use, in this case, I'm supposed to use F sine theta with the vertical height, but this is also not a part of your, so F cos theta with the vertical height, which is also not part of your answers. So in that case, we cannot use this one. They're using the most easiest method. They're using basic trigonometry here. If I just delete all these things, I want to find out the distance on the plane, right? So this is the distance I want to calculate. This creates a right angle triangle. If this is a right angle triangle, then I'll just write this down over here. This is your 90 degree, this is H, this is D, and this is sine theta. Opposite over hypotenuse, obviously we're going to use sine theta with H by D, or D, the opposite by D. In that case, you get the value of your D as H over sine theta. Now we have the force acting along the plane also in the direction of your distance, which is F newtons. We'll use the easiest equation. Work done equals to force distance. So you have force is force, distance is delta H over sine theta. So it will be just F delta H over sine theta, right? So this is going to be your answer for option D. The easiest method that they use for trigonometry, not any force distribution they used over here. Is there any problem from question 9?
No.
If there is no problem, then we'll quickly move on to 10. When compressed by a force of 50 Newton, a spring had a length of 12, and when compressed by a force of 70 Newton, the spring had a length of 7.1. Which of the following expression gives the stiffness K of the spring in newtons per centimeter? We don't need to change the unit, but over here I'm trying to find out the value for stiffness. Stiffness is what? Force K delta X. So in order to find out K, it will be F divided by delta X, right? So change in F and change in X that we have to use. Change in F is 70 minus 50 divided by, at 70 at 7.1. So you have to write, but then again, extension is a scalar quantity, right? As obviously I can understand they're getting compressed. So extension is supposed to be negative. So I will just write this as 12 minus 7.1, because stiffness is also a scalar quantity. So that's why extension over here is supposed to be a scalar quantity. I mean, it doesn't have any direction. So I just wrote that, 12 minus 7.1. It won't be a matter for this calculation. So we get our correct answer as option B. And we know for compression, extension was supposed to be negative, right? So that's why that's not a problem, that even if you're subtracting 7.1 from 12 or 12 from 7.1. Okay, then we are done with your question 10 also. After this, we'll quickly move on to section B, but I don't think we'll be able to finish that. That means we'll continue with this in our next class, okay, which is on Monday, hopefully. Okay, but we can finish this question. A disk of mass m is held stationary by a force exerted by a magnetic base as shown. Okay, the free body force diagram for the disk is shown below. And basically what is happening, this table is a magnetic base and this is a disk, right? Obviously weight acts in the downward direction and a magnetic force is acting in the upward direction. So these two forces, weight and magnetic base, they are balanced with each other, and that's why the disk can, actually float in air without any visible forces acting on it. So they're saying that which two forces are, so the two forces are equal in magnitude and opposite in direction. And we have to give two reasons why these forces are not a Newton's third law pair. In order to be Newton's third law pair, what was the cases? I'll write down the list again. In order to be, for any force to be Newton's third law pair, obviously they must be equal in magnitude. That was your case, equal in magnitude. Then opposite in direction. The other one was that, have same line of action. That means they both must act in the vertical plane or horizontal plane. And then again, equal magnitude, opposite direction, same line of action. And what else? Must act on two different bodies. And then again, after this, the forces must be of same type, right? Same type forces. Problem is, these 2 points are not matched for your question 11. The forces are not acting on two different bodies. The magnetic force is also exerted on the disk, and the gravitational force is also exerted on the disk, right? So we're talking about two forces acting on the same object. Another thing, these are two different forces, right? Weight is gravitational force, magnet is magnetic force. So they are not of same type also. Because of these two reasons, we cannot consider them as Newton's third law. Instead, they are now Newton's first law, right? When oh wait, they're not even Newton's first law, because the forces are not of same type again. So I'll write down the differences or list of quantities for Newton's first law again. This is just for your notes here, right? This is not related to your 11. I'll write down the answer for 11. Only difference is now this should be same forces. Sorry, 1 minute. On same bodies, right? Okay, this is your Newton's first law pair. Now over here, this is neither Newton's first law nor Newton's third law, because this also doesn't matches, right? If this was matching, then I could consider, okay, this is a Newton's third law pair, first law pair. So I'm just going to say that forces are acting on the same object, and they're of different type, as weight is gravitational and magnetic, and what was that? And upward force is magnetic force, right? And the forces were magnetic force. Is there any problem from question 11 from anyone?
No teacher. Amish.
Not teacher.
Okay, then if we quickly move on to your question part B. The magnetic base has a weight W and rests on a horizontal ground. Complete the free body force diagram below or for the magnetic base. Okay, I can understand that obviously magnetic base will have its own weight, but now you have to understand that if there was if this what was that? If this magnet was exerting a magnetic force onto the disk, that means the disk was also providing some magnetic force back onto the magnetic base. So we have a downward force acting on the magnetic base that is coming from the disk, right? And again, since the magnetic base is in contact with the ground, so it will have a reaction force now. For this disk, it was not in contact with the magnetic base. That's why for this disk, it didn't have any reaction force in the upward direction. So we're going to write that over here, and also this was also balanced, right? That means this upward force was also of equal magnitude with the downward force, right? They must have the equal magnitude. In the upward direction, you have your reaction force, and in the downward direction, in addition with your weight, now you have a magnetic force that is exerted by the disk also, because obviously at that point some Newton's third law pair will happen. If the base provides the upward force onto the disk will also provide some downward force onto the base, right? So this is a force, magnetic force from the disk onto the base. Is this clear? Any problem from question 11b?
No teacher.
Not teacher.
Okay, then we'll quickly move on to 12. What is meant by the term elastic limit? Repeated question, right? We just have to memorize the definition. It is the force, or it is a region, for the graph where force and extension graph is linear and the object return to its original length, right? Or we can say it is a force beyond which the cable does not return to its original length when the applied force is removed. Up to this limit, so beyond this limit, we should write. They're talking about cable here, so we should write down the material as cable. Beyond this limit, the cable does not return to its original length applied force is removed, right? After this, they're saying that the elastic limit of a steel cable was reached when a force of this much was applied and the extension of the cable was this much. Length of the cable is this, cross-sectional area is this. Calculate the strain of the cable. Strain is what? Extension over length. Extension is 0.126 divided by 6, right? You just have to divide this to get to the value for your strain. 126 by 6, that leaves you with 0.021. So you get 0.021 meter. One thing to understand that over here, they have used 3 significant figure, 3 significant figure, 3 and 3, but I got my answer as 2. So I'll just write it like this, okay? Because I cannot obviously increase my significant figures. So I'll write 0.021 meter. After this, now they're asking to calculate the stress in the cable. Stress is just force over area. For force over area, they gave you the cross-sectional area directly, so nothing else to calculate. 13.4 into 10 power 6 divided by area was 9.6 10 power minus 3. So you have 13.4 10 power 6 divided by 9.6 10 power minus 3. And that gives you a value of a very big value. I mean, we get the actual value on my calculator is 13958333333 what pascals here. The problem is the maximum significant figure used was what? 3 significant figure, right? That means I can also keep my answer to 3 or 2 significant figure. So if I round this up to 3 significant figure, I get 1.40 10 to the power of 1 2 3 4 5 6 7 8 9, right? Into 10 to the power of 9 pascals. So we get 1.40 10 to the power of 9 pascals. Any problem from question 12 from anyone?
Not it.
Not it,
Oh.
teacher.
No, teacher.
Then we'll quickly move on to 13. Yeah, we can finish 13 today. Over here, a coat hook is attached to a smooth door by a screw as shown. The diagram below shows 3 of the forces that act on the coat hook and when a coat hook is hung from it. And the weight of the coat hook may be neglected. Okay, door, weight of coat, vertical force from screw, and a label diagram to show a arrow to the diagram to show the additional force required to the coat to be in equilibrium. Obviously, weight of this and vertical force are balanced, but this horizontal force from screw is not balanced with the reaction force, right? So obviously, there should be a force of equal length in the opposite direction. So this is your reaction force. I'll just write this as R, okay? In the diagram, you can just write this as R, no problem. This is your reaction force. Now all the forces are balanced. Horizontal force is balanced, vertical force is also balanced. Now after this, are they only giving it 2 marks? Add a labeled arrow. Yeah, labeled arrow, right? We labeled it and then, so in that case, instead of giving a labeled arrow, I should just write this in terms of words, reaction force. Okay, then this is it. One mark for the arrow to the correct direction length, and then 1 mark for the written force, labeled arrow, labeled force. Okay, after this, now they are saying if too many coats were hang onto the coat hook, the hook will rotate and pull the screw out of the door. Um, okay, and pull the screw out of the door. Point P is a position of the pivot as shown. This is the pivot. And the maximum horizontal force, the screw is this. Horizontal force, this is the reaction force they're talking about, right? The maximum horizontal force that this coat can have. The mass of one coat is this. Deduce whether a person could hang more than 2 of these coats from the hook. We have to identify. Okay. Weight of the coat was 2.5 centimeters away from the pivot. So 2.5 centimeters horizontally away from the pivot and 0.9 meters below the horizontal force on screw. If too many coats were hung on the coat hook, the hook will rotate and pull the screw out of the door. Okay, in this case, this is happening. Basically, your reaction force and your weight of the coats are actually, making the entire hook over here rotate. You have to understand this will rotate the hook in the anti-clockwise way, right? Yeah, this will rotate the anti-clockwise way. That will be able to keep the coat hanging there, and this will rotate it in the clockwise way. And if this rotates in the clockwise way, then only the entire hook will rotate and pull the screw out of the door. So we cannot have this to happen. Right? That means equilibrium must be maintained. For how many weights you have to understand. So if equilibrium is maintained, that means obviously your moment moment clockwise should be equals to your moment anti-clockwise here. So for your moment clockwise, what are the forces? Weight of the coats, I do not know. I need to find out that what is the maximum weight of the coat that this equilibrium arrangement can hold. So you have weight multiplied with how much was it from the overall pivot? It was actually 2.5 centimeters. If you consider that as meter, it will be 0.025 meter, right? And then again for your anti-clockwise moment, we have this 150 Newton reaction force. That was again 0.9 centimeters. It's going to be 0.009 meters away. If I make W the subject, we get 150 0.009 divided by 0.0025. But if you calculate this, you get 54 Newton, right? If this is 54 Newtons, and the maximum mass that we can adjust is 2.6. That means weight is 54. So I can also break this down as W equals to 54. Then the mass will be 54 by 9.81. So from there, we get the value of your mass as 5.50 kg. Now, if you divide this with 2.6 to find out the number of coats, that's going to be 5.5 divided by 2.6, and that leaves you with 5.5, 2.6. This is 2.12 coats, right? Which is approximately 2 coats. So obviously, this hook can actually, withstand 2 coats on maximum and not more than that. So you have to write down a statement here also that a person could hang only 2 coats, not more than that. More than that. Is this clear? Any problem from this part?
Not teacher.
Okay. Then we are done with your question 13, and from question 14 onwards, we will have to start from our next class, which is going to be on Monday again. Right? Just 1 minute. Assalamu alaikum, everyone. Today we're supposed to continue with the June 22 paper. Right now, I think so many of you couldn't actually do the first part of the class. I hope all of you watched the recordings for this June 22 part 1, where we solved the initial 13 questions. So for the Jan 25 batch, do you guys have any problem? So you guys watched the recording entirely for this part. Do you guys have any problem from the initial 13 questions?
Ma'am, I didn't understand one.
Wait, sorry, Safia, I cannot actually listen to you. My mic is not working. 1 minute. Yeah, can you repeat again?
Ma'am, one MCQ about the series and parallel string. I couldn't understand that.
Okay, sure. 1 minute. This one, right? Okay, in this case, if I draw this working again in a separate page. Okay. In series connection, we have two. This is your spring 1, and then again on this we have another spring, right? So this was your series connection because both the springs were connected using the same force, and same force acts onto them, right? So over here, each of the wires are going to extend by delta x this time, right? So this is going to extend by delta x, this is going to extend by delta x. Now if you talk about a normal wire, when you are focusing on only one wire and only on one wire you're applying a force of F newtons, for those cases I get to use the equation of what energy is equals to half F delta X, right? And then again, I can break down F also in terms of your spring constant, because in series and parallel, the equation that is actually important, or the quantity that is actually important, is your spring constant, right? So I can also write this as, okay, F is equals to K delta X. So if this is my equation 1, this is my equation 2. I can write this equation, substitute them together to write it as F K delta X, and eventually it will be half K delta X whole square. I'll just write this as delta X square, right? Now this is the equation that you get. I think that term they used, 1 minute. Yeah, the term that they used for energy was actually capital E, right? And there we had two springs, I think, right? P and Q, P and Q. Yeah, we have two springs, P and Q identical, and the energy was objected when the force was F newtons on each string was capital E. Okay, then in that case, this is they're considering as E. The value for E is half K delta X square. Now in this case is what happens. F is same amount of force is acting on both the springs, and because of same amount of force, now I'm getting how much extension? Twice the extension, right? So for twice the extension, the value for your E also in just 1 minute. So for twice the extension, the value for your E should also be multiplied with 2. So in that case, if I want to find out the extension for this case, total extension, I'll consider this as what? I'll just consider as series connection, right? So series for S. So for this series connection, we have extension like energy for particle P, and then again energy for particle Q. Sorry, for particle Q. For energy of particle P, what do we have? Half K delta X square, and then again for this one we have half K delta X whole square. Half and half, if you add them together, you get 1 delta K X square, right? And how do we get 1 delta K X square? If I want to represent this in terms of E, that means somehow I would have to extract this equation out of this, right? So this was half delta Kx square was E, and now we have 1 delta Kx square. And how can you get 1 delta X square? By multiplying. I mean, I can write this first, 1 delta 1K delta Kx square and delta X square. And then after this, I can break down this 1 as 2 multiplied with half K delta X whole square, right? So from there, I can understand that half multiplied with 2 eventually restore your 1. But the main motive of to break down this 1 in terms of 2 multiplied with half, so that I can write this statement. And this expression is what? Capital E. So we can get 2E for the series connection. Is this clear, Safia? Any problem from this part?
No.
Then for the parallel connection, we again have the same wires P and Q, but this time for the parallel connection, this is one wire and this was your other wire, right? From this wire, force of F newtons was again applied. This time you have to understand that not the total force was acting on each of the wires, right? Half of the force was acting on both of the wires because the force is now equally shared. If the force is half, the spring constant always remains same, remember that. If spring constant remains same, that means extension is also half. So in this case, the equation for them is actually F over 2, that is equals to K delta X over 2. Right, this is the, this is how the situation is going to be, K delta X over 2, right? And if this is the case, if the value for your F is now F over 2 or Kx is going to be Kx over 2, from there I will have to write this as, again for the total energy, I'm going to consider this as P. Oh no, 1 minute. P is already used. Let's just use R over here, okay? Random words I'm using. For random words, the total elastic strain energy for first spring in parallel connection is going to be half. It was F over 2, right? So F over 2 means, now we have 1 minute. Yeah. In this case, what do we actually have? F over 2 multiplied with delta X over 2, right? If you understand the derivation, this is how we're going to start. After this, I will break down this F in terms of K delta X. So we again have half. Instead of F, I'll break this down as K delta X divided by 2 multiplied with delta X divided by 2. And this entire thing will get repeated for the other particle or other spring, which is also connected in the parallel combination. So we have half F over 2, then delta X over 2. And obviously from there also I have 1, 2, K delta X over 2 and delta X over 2. Right, so after this, if I simplify it, we basically have 1 by 8. 1 by 8 K delta X square, and then again 1 by 8 K delta X square. And how much is this 1 by 8 and 1 by 8? They're going to restore your value for 1 by 4. Right, so I think that was the answer, I think, right? Oh, sorry, I have to restore that original E also. Sorry. I mean, from there I get 1 by 4. That's fine. But problem is, this is the value for your R, right? For the parallel combination. I have to express this in terms of the value for your E. The value for your E was half Kx squared. So I have to break down this 1 by 4 into half K delta X squared. That was your value for your E, so you get half E this time. In parallel combination, elastic stored energy decreases by 2, and in a series connection, elastic strain energy increases by 2. So this is the overall working. Is this clear now, Safia? Any problem?
Yes, ma'am. Thank you.
Okay, anyone else who have any questions from the previous 13 questions of this file?
No, teacher.
Okay, if there is no problem, then just 1 minute. I am not sure how to pronounce this name, but I think it's Tesandu, right? How do you pronounce this name?
Yeah, teacher.
Okay, then yeah, sorry. So Tesandu, now this is, you missed the last class, and I also couldn't give you the recording maybe for the previous questions. Okay, so you will have to watch the recording after this class ends.
Okay, teacher.
Okay, and again, if you have any problem, we can discuss that problem maybe at the start of our next class or the end of your next class.
Okay, teacher.
Okay, so we're going to start with question 14. For 14, this is what? A refrigerator braking, a regenerative braking system allows an electric car to use a kinetic energy to charge a battery as the car decelerates. The car traveling at this decelerates to rest. Obviously, final speed is 0, initial speed is this 13. The energy transferred to the car's battery during this deceleration is this much, so energy is given. Efficiency of the regenerative braking system, mass of the car is this. We want to find out the efficiency of this regenerative braking system. Allows an electric car to use its kinetic energy to charge a battery as the car decelerates. Okay, and the energy transferred to the car's battery during this. I mean, over here, this is the energy received, right? I mean, basically, the amount of energy transferred as a useful part is this is like they're using this, like the energy transfer to the car's battery in order to charge it is this much, 73.9. So if this is your energy input, I have to use your like, so this is your energy output. Yes, this is your useful energy output. Like out of the total energy, whatever the car is creating during the deceleration process, only 73.9 kilojoules of energy is actually used in order to, like, do the main work. The kinetic energy of the deceleration is used to charge the battery now. But how much total kinetic energy was actually used during the deceleration, that you have to calculate. I can easily calculate that, since over here they have given you the idea that, velocity is given and not exactly, yeah, I mean, over here they have given you the velocity and mass is given. But in this case, like, half mv square, I can find out that exactly the initial start, when the car was moving or starts to decelerate, how much was your total energy at that point. So your energy input is actually the total energy of the initial point. That is your total energy input, like how much energy the car actually produced, and out of which, how much is actually being used in order to charge the car's battery. So this is going to be half 1560 multiplied with velocity is 13 square, right? So from there you get 1560, 13, 13, 0.5, and that is 13,180 joules. This is a very big amount of energy that is actually produced by the car during the deceleration process, but only 73.9 kilojoules was actually used to charge the battery. So if I want to find out the efficiency, I just have to, like, what? Efficiency of the regenerative system, right? They didn't ask you for the percentage. So I just have to use 73.9 into 10 power 3, dividing this entirely with 131820. So you have 73.9 10 power 3, then divided by, 73.9 10 power 3, dividing this by 131820. So you get 0.56. This is your efficiency, that only 0.56% or 56% of your total kinetic energy is transferred into the car's battery charging. Is there any problem from this part A?
No.
No.
Not issue.
Okay, then if we move on to the next question, the drag force on the car as it moves through the air. 1 minute. Yes, Aisha, you can ask.
Miss, we can leave it as a percentage, right?
They didn't ask you to calculate as a percentage here. I mean, but you can, yeah, sure, no problem.
Okay.
Okay, then moving on to the next part, drag force acts on the car as it moves through the air. So state how the drag forces vary with the velocity of the car. In this case, I can understand, I'm not in this case, in general cases, they're talking about like how drag forces vary with the velocity of the car. We know that, drag force is directly proportional to the surface area and velocity. So if any of these things, surface area or velocity is increasing, drag force is supposed to increase. This is a repetitive question you can think of because this is a conceptual question, doesn't have anything to do with the understanding, right? So we just, as velocity increases, drag force increases, this is enough, writing this much is enough. As velocity increases. Okay, then after this, it says that graph shows how the efficiency of the regenerative braking system depends upon the initial velocity of the car for initial velocities within the range of 20 to 40. Like it says that, if the initial velocity, in this case, the initial velocity was 13, if you remember, right? From 13, it starts to decelerate. It says that how the efficiency of the regenerative braking system would be if the the system depends on the initial velocities of the car for initial velocities within the range of 20 to 30. Like they have given you that within the range of 20 to 30, like if you carry out the experiment where the initial velocity was 20 and all the way to a second experiment or to a fifth experiment where the initial velocity was 40, For those type of data, this is how the graph looks. Efficiency kind of what drops down as the value of your velocity increases, right? Because over here, if I label this, like randomly I'm labeling this, okay? So if this is your initial velocity 20, at smallest initial velocity, you get the maximum efficiency. At largest initial velocity, you get the smallest efficiency, right? Because efficiency kind of slopes down as your value for the initial velocity increases. That's what we can understand from the shape of the graph. Other than this, it says that explain why the efficiency of the regenerative braking system varies as shown in the graph. Like over here, it says that why the initial velocity, increase in initial velocity decreases the efficiency. Like it says that why increasing initial velocity means that only less amount of the total energy input is actually used to charge the battery. That's because as your speed increases, air resistance increases, right? Air resistance through which you're moving, that increases. That means the more, for a larger air resistance, you have more of your total energy that is going to be used up to overcome the air resistance. So more energy is dissipated to overcome the air resistance, leaving very small that should be used to charge up the battery. That means more of the energy is actually wasted, right? I do not need to actually move against the air resistance. I mean, I have to, obviously, in order to move forward, I have to move against air resistance. The problem is that is not doing anything for me. Moving against air resistance is not a beneficial thing for me. Sorry, as I was saying, moving against air resistance is not a beneficial thing for me, right? Moving against air resistance means now more of my input energies are getting converted into waste energies. Moving against air resistance, that is a waste energy. And only small portion of my energy is now getting used to charge up the battery. So this is how the energy is actually getting used. If I draw a Sankey diagram, even though it's not part of my syllabus anymore, right? This was in part of your IGCSEs, not part of your O-levels, A-level syllabus. You can now understand this is how it would look. 1 minute. Right, this is your waste energy. The higher the initial velocity is, the more energy is getting used or dissipated to, work against air resistance, and less energy is available to actually charge up your battery, right? And this is your total input energy, which, by the way, depends on the value for your initial velocity, right? So in this case, you can see that obviously at higher speed, total input energy is big, but at higher speed, air resistance is also big, which means that more of the energy is now being used up to work against air resistance, or is now dissipated to move against air resistance, to overcome air resistance, leaving only a small portion of the input energy to charge up the battery. So obviously the efficiency decreases. So I'll write down the answer. They're giving you 4 marks for it. Increasing initial velocity increases the total energy input to charge the battery. Is there any problem from this question 14? This is, by the way, the end of your 14. Oh, and obviously decreasing the efficiency. We have to also state that. thus decreasing the efficiency. Okay. Any problem from question 14?
No, teacher.
No.
Okay, if there is no problem, then now we'll move on to question 15. I hope there's no problem. Anyone have from this question 14? Then this is a star mark question, right? These are the most important types of question because they're not only your mark scheme point will be mattered. I mean, obviously in all the questions I have to always write my answer exactly to the mark scheme word. But this time I also have to make sure that my answers are well organized. Like my points are actually related to each other. I do not write my first point and then automatically move on to fifth point and then again come back to my fifth point. Okay, third point. That's not how I can arrange my answer. The arrangement of your mark scheme point, the logical arrangement of your mark scheme point is very important for these questions. So if I talk about how many marks they're giving you, 6 marks they're actually giving you. This time, in most cases, star mark questions can have a mark from a range of 4 to 6 mark. This is a 6 mark question. It says a Galilean thermometer consists of a closed glass cylinder containing a liquid. In the liquid, there are several identical sealed glass bulbs as shown, and attached to each bulb is a metal disc labeled with a temperature, which disc has a different mass. Okay, so these are glass bulbs and these are metal disc, and metal discs also have a different temperature. So we can see that this is what glass bulbs with temperature at 22 to 23, they tend to fall to the bottom of the entire glass jar, whereas glass bulbs with temperature from 25 to 26, they tend to move at the very top level of your what is this glass jar, right? Glass cylinder. It says that the temperature increases, density of the density of the liquid decreases. This can cause the bulbs to move within the liquid. Okay, they're saying that as temperature decreases, density of the liquid decreases. If density decreases, that can cause the liquid to move. Let's think about it. If the temperature decreases, in that case, and also in that case, if the density of the liquid decreases, density of the liquid is very important for your upthrust.
Miss, it said that as the temperature increases.
Sorry. Yeah, sorry, just noticed that it increases, sorry. In that case, as temperature increases, density decreases, right? So if density is decreasing and in upthrust, you have the equation rho g v, right? G is a constant value, gravitational field strength. V over here is also a constant value because in this case, V represents, glass bulbs are not regular structure, right? These are irregular structure. That means in order to find out their volume, I would have to use the displacement method. If all the bulbs are already entirely submerged into the water of this glass cylinder, that means obviously volume of the displaced water by each bulb is equals to the volume of the glass bulb itself. So volume is also constant, gravitational field strength is also constant. And if they're saying that for a higher temperature, you get a smaller density, that means you get a smaller upthrust also, right? So basically, we can say that, for a smaller density, you are supposed to have a, smaller upthrust. If you get a smaller upthrust, then inside any liquid, there are two forces acting, right? Weight and upthrust always. So if you're focusing on these two forces only, and in that case, what happens? Weight is always constant, right? But depending on the value of your upthrust, the motion of the glass bulb can happen. So in that case, what will happen? At a higher temperature, when the density is lower, at that point, your upthrust is also smaller, right? If at a smaller upthrust means that now, maybe at some point, your upthrust will go smaller than the weight. If your upthrust is smaller than the weight, in that case, weight is greater than upthrust. If weight is greater than upthrust, then the bulbs over here or glass bulbs over here is supposed to sink down, right? Not move up. And what is there saying? Explain why a particular bulb will float and until the temperature of the liquid exceeds a certain value. Why they will float until it exceeds a certain value? Because at some certain value, this is the threshold temperature. At that set threshold temperature, upthrust will be up to that upthrust was greater than weight, right? That's why the bulb will continue to flow. And after that point, when the temperature increases that level, then the upthrust will become smaller than weight. When upthrust is smaller than weight, the bulb will again sink, right? Is this clear, the explanation for this entire process?
Yes, miss.
Yes, you.
Yes, miss.
So we can first talk about that inside a liquid, only two force acts onto this glass bulb, right, which is upthrust and weight. And again, weight is a constant weight force, right? The value for your weight never changes. Doesn't matter wherever you are at the top or bottom of the glass jar, of the glass cylinder. And again, we can see that since at higher temperature, what was that? Yeah, at higher temperature, density decreases. Density is related for upthrust, or density is what was that? Density is, upthrust depends on density. So when density decreases, upthrust also decreases. So whenever the temperature exceeds that certain value, after that certain value, density is so small that upthrust also becomes very small, that is even smaller than the weight, making sure that weight resultant force is now in the downward direction, eventually pulling the glass bulb down. And before that certain value, density was high, upthrust was larger than weight. That's why the glass bulb could float up to that certain value of density or temperature. Beyond that, the glass bulb will sink. This is how you're supposed to arrange your answer over here. So if we start with that, inside, 1 minute, if it was talking about water or not. They're not specifically saying if the liquid is water, right? So it's not wise to use the term water. So I'm going to say inside the liquid, that is weight and upthrust. Upthrust can change. Temperature increases, density decreases. Decreasing the value of upthrust up to certain value. Temperature of the liquid exceeds a certain value. Yeah, up to certain value of temperature, upthrust was, in that case, in order to float, basically, right? They're saying it will float, not that it will move upward, right? So if it is floating, that means at that point, up to before that certain point of temperature, upthrust was actually equals to weight. If it's floating, floating means the overall resultant force is zero. Upthrust is equals to weight, right? So you have to see that up to certain value of temperature, upthrust was equal to water weight of liquid, or we can say that weight of liquid displaced by the glass bulb, or we can also suggest the weight. No, let's just stick to the bigger versions of the terms because they're giving a 6 mark for it. Up to certain value of temperature, upthrust was equals to weight of liquid displaced by glass bulb. Glass bulbs where resultant force, I write resultant force as RF, right? So RF represents resultant force. Resultant force is 0. So bulbs can float beyond the certain value. Beyond the certain value, upthrust is greater than upthrust is less than weight, making the resultant force in the downward direction, or creating a resultant force in the downward direction, making causing the bulbs to sink. Right, beyond the certain value, upthrust is less than weight of liquid displaced by what? Displaced by glass bulb. Producing a downward resultant force and making the bulb sink. Right? So this is your final answer. I'll give you guys 2 minutes to read this entire passage and let me know if there's any problem.
Miss, can you show its question as well? Only the question, not the entire first part.
Okay, sure. Yes, Carl, you can ask.
Miss, isn't the weight of the liquid displaced similar to upthrust? Isn't that the upthrust?
Where? I'm sorry, 1 minute.
The weight of the liquid displaced.
Hmm?
Isn't that the upthrust?
The weight of the, in this case, basically we're saying that over here, the weight of the, liquid displaced, that is, yes, that is equal to the upthrust. Oh, wait, in that case, it should be written weight is less than the weight of the glass bulb only, right? Over here, it's supposed to be only the glass bulbs. Right, not about the liquid displaced by the upthrust. But in general, actually, upthrust is actually the value that you get obviously after the weight of the water, of the weight of the liquid that is displaced by the glass bulb, right? But then again, the weight at the maximum point, or up to before the certain value, your weight is equals to the upthrust acting onto the bulb also. That's why the bulbs could float easily. Right, so that's why I wrote that 1 minute up to certain value of temperature, upthrust was equals to the weight of the liquid displaced by the glass bulbs. But when we extend that value of temperature, then upthrust become less than the weight of the glass bulbs, and eventually there's a resultant force in the downward direction, making the bulbs sink.
Oh,
Is
yeah,
this
I get it.
clear?
Yes, Miss, thank you.
Okay, I'm going to wait for a few minutes for others to continue, and then we will move on to the next part. This was the end for your question 15, by the way. Okay, if there is no problem, then we will move on to question 16. Is there any problem from anyone?
No, miss.
No.
Um,
No, miss.
Okay, then we will move on to question 16. There it says a student is flying a kite. The kite is held in equilibrium. All the forces are balanced by a string as shown, and we can see there's a tension of 70 Newton acting 45 degrees from the vertical plane. Weight is 24. Not to scale diagram. Determine the magnitude of the tension in the string by using a scaled vector diagram. Okay, I have to draw a scaled vector diagram. I can roughly understand that if 70 Newton is acting at a like, and this is what, if I distribute this into 4 quadrants, 70 Newton was acting in the like what is this? In the first quadrant, right? Weight is in the vertically downward. We need to find out the tension in the string by using determine the magnitude. So wait 1 minute. What is 70 Newton? Wind exerts a force of 70 Newton. Okay, sorry. Wind exerts a force of 70 Newton over here. I want to find out the tension. But again, I can understand that in this case, tension will also not be in the vertically upward plane or something, right? Because the weight of the kite is 24, then the wind exerts a force of 70 Newton, this much angle from the vertical as shown. And the string over here was also, I mean, if I distribute them, I can understand that obviously, oh wait, tension in that case over here, this is your what was that, wind, 70 Newton force. This is your weight, 24 Newton force. You have to understand the wind wants to pull this kite away from the boy, right? But the tension is the one who is holding the kite over here. So tension acts in this direction. So if tension acts in this plane, I have to rearrange these three triangles, these three arrows in order to create a triangle. So I can understand this is how the weight is going to be vertically downward. This is your 70 Newtons 45 degree inclined, 70 Newtons 45 degree inclined. Now I do not know exactly how much inclination this tension is from the vertical plane or from the horizontal plane, right? But I can understand that if I can, ex extend this to the first quadrant, this is how the triangle is going to look. So I have to basically find out this, find out this angle and this magnitude, right? I'm just going to write this down over here. This is, by the way, 43 degrees. This was your 70 Newton. And this is your vertically downward, 24 Newton. This is the theta that you want to calculate. And this is your, this is your tension that we want to calculate over here, right? I have to find out the tension. I have to find out the theta also. So in that case, if I have to calculate all these values, I have to draw a vector diagram this time. And from the vector diagram, determine the magnitude of the tension. Okay, if I'm using a vector diagram, right, then I just have to draw exactly this shape, but we have to make sure that my angle between this what was that, air resistance and weight is exactly 43. I have to measure this angle using this using a protector. You can measure this angle, right? And again, after this, you have to use a scale to represent the 70 and 24. Now, obviously, I cannot consider 70 as 24. That's a very big value to represent it on a diagram. So I have to use a scaling here, right? For that scaling, I have to represent 70 Newton as your 7 centimeters and 24 Newton as your 2.4 centimeters. So after plotting this length for 70 and 2.4, I'll be able to easily measure this line length of the tension. Whatever the tension that I get, I just have to whatever the length that I get for this tension line, I just have to multiply 10 with that to get to your final actual value for your tension, magnitude of your tension. Okay, just give me 1 minute. I need to open another app to show this question. Just 1 minute. Okay, I already understand that what the basic structure for my triangle is going to be. So I'm going to first, draw the vertical line, which was for 2.4 centimeters, right? I'm going to draw the vertical line for 2.4 centimeters. This is roughly a straight vertical line we can consider. Okay, this is now a straight vertical line. The length of my vertical line is supposed to be 2.4 centimeters, right? So 2.4, I cannot actually, I do not want to start with 0 because then the graph will be very on the rough top parts over here. I'm just going to pull this little down. And then I'm going to plot a graph from 0 to 2.4, right? Exactly there I will stop. This is your vertical weight acting on the kite, right? After this, if I want to draw the graph from this part, if I want to draw that 70 Newton 43 inclined, then I'll have to draw that outside the graph. So what I can do easily is that I can draw that 43-degree inclination, and from there I can plot a line. So 43-degree inclination means I have to make sure this is exactly here. 43 is somewhere here, right? Yeah, this is 43. Roughly that is 43. If that is 43, I'll remove this, and now I will have to connect the scales. Just 1 minute. Okay, now after this, I have to now plot a line for 7 centimeters, right? So for 7 centimeters, we're going to start with 0 and go all the way to this point, and this is it. Right, if I can draw this one, after this, I just have to connect the two ending points of this triangle, because I already know this is a vector diagram. Whatever the length that I'm going to get here, that is going to be your actual length for the tension over here according to your scale diagram, right? This time, right? I'm not calculating this. I can now directly get this from the scale diagram. How much do I get on my diagram? This is from 0, and this is exactly at 5.6, right? So this is your 56 Newton in that case. I got 5.6 here. So I just have to connect this, and 1 minute. Yeah, I'll just consider that as my answer actually, because if I want to redo this, it's going to delete all of these things. So let's consider this. This was my air resistance of 70 Newton, but length was 7 centimeter here, right? This is the direction of your weight. Weight was 24 Newton, and this was upward and this was downward. By the way, this angle we also calculated, that was 43 degrees, right? And then again, this is what we got after the measurement as 56 Newton. Is this clear? Any problem how we draw this diagram and got to the overall shape over here? Any questions from this part?
No, miss.
Okay.
Not
In Okay. In your exam paper also, you have to draw this type of structure, and obviously with that structure, you have to label the scaling also. Like what is the scaling that you're using on the side of your working, you have to say that the scaling is 70 Newton is represented as 7 centimeter and 24 Newton is represented as 2.4 centimeters, right? So this is the value that we're going to get. On your diagram, I'm never going to write that 7 centimeters, 5.6 centimeters, or 2.4 centimeters. On your diagram, you will write the actual values of the forces of vector quantities you're working with. This is a vector diagram. Other than this, we don't actually have anything else to do. So we're going to stop here. After this, if we move now to part B, the student wants to determine the tension in the string. She attaches a mass holder to the string. The student adds non-masses to the mass holder until the kite is in equilibrium and part of the string becomes horizontal as shown. Okay. So this is how the entire thing would look. And now it says the student takes a photograph of the arrangement. Describe how the student can use this photograph to determine the value of your T. If the student wants to find out the value of your T, then first thing I have to obviously take, I mean from the photograph, right? It was already stated the student took a photograph of this entire arrangement, right? So since it is on a photograph, then I can now take measurements from the diagram also. So first, obviously, the mass holder creates weight here, right? So I have to calculate the weight using the mg equation, W equals to mg equation. That will calculate the value for my weight that is hanging from the mass hanger. And again, this time, I can understand that over here, I can distribute this into 4 quadrants, right? Vertical, upward, and horizontal, left, right. In this case, from the photograph, I can now use a protractor to find out this angle, whatever this theta makes with the vertical plane. In that case, tension over here is going to be T cos theta, which is actually equal to your weight. If we have the value for your theta, then I just have to do what? I can already understand the object is in equilibrium, right? So in the vertical plane, it was equilibrium. If it is equilibrium in the vertical plane, then we just have to use the equation resultant force equals to 0, where we have T cos theta minus mg, or which was actually the value for your weight, equals to 0. So you end up getting the value for T as mg over cos theta. Using this formula, now the student can calculate the value for your T from the photograph. Is this clear?
Yes, miss.
Yes, teacher.
yes, miss.
Okay, then we are going to write that as tension was acting, as tension was not acting in the vertical plane, so you have to take measurements from the photograph. What was the angle between the tension and the vertical plane using a protractor? With the vertical plane. After this, we have to talk about that, the angle it makes with the vertical plane. After this, we can say that the vertical plane is equals to the weight from the mass hanger They're only equal to each other. The vertical component of your weight, so the vertical component of your tension is only equal to your weight because the object was in equilibrium, right? If it was not in equilibrium, then we could not have stated that as it was in equilibrium. So from there, we can get the equation from RF equals to 0, T cos theta minus mg equals to 0, T equals to mg divided by cos theta. Can calculate tension. Right, just referring to this entire equation will be enough to explain the final case. Like, vertical component of T is equals to weight. We've already stated that. Now, after this, from the equation RF equals to 0, if I make T the subject, this is how the equation looks like. And from there, we can easily calculate the value for your tension acting from the photograph on this kite. Is this clear? Any problem from this question 60? Yeah, this is the end of 60.
No, teacher.
No.
Okay, then if we move on to your next questions. This is what I think this is about momentum, right? Yeah. Collisions using answers. Okay. The diagram shows two bumper cars, P and Q, at an amusement park. Q is stationary. P is moving at a speed of 2.1 towards Q. Okay, so this is the case. This was not moving. This was moving with a velocity of 2.1 meters per second in this direction. And P collides with Q. After the collision, P and Q move off in the same direction. And P move with the speed of this much and Q move with the speed of this much. Show that the total mass of Q was about this much and the mass of P is given. I mean, if I just draw a very simple diagram, right? This is the same cases you see in your M1 also. If you guys have M1, then, it's very easy to solve. PQ, PQ, before collision, after collision. For before collision, the mass was 250 kg. I mean, everywhere the mass is same, right? Mass doesn't change during collisions or anything. So this is mkg. This time it doesn't have any velocity. This only had a velocity of 2.1 meters per second. And after collision, they both move with the same direction with different velocities. What I can understand is that, over here, all the velocities are in the same direction. So since everyone is to the right, so I also consider the direction towards right as positive. If that's the case, total momentum before collision is equal to total momentum after collision. And from there, you have 250, 2.1. This one is going to be 0, right? Because initial velocity of Q was 0. So m0 is 0. So we get plus 0. And then again, 250, 1.15 plus m 1.57. From there, if you just make m the subject, it will be 250, 2.1, 1.15 divided by 1.57. I just rearranged the equation, right? I hope the rearrangement is clear for everyone. Divided by 1.57, that leaves you with 151.23 kg. So 151.27 kg, which is roughly 150, right? In this case also, they are saying your answer should be very close to 150, not exactly 150. Another thing to understand, all of the significant figures that they used over here was how much? 3 significant figure, the maximum that I can see, and the minimum was 2 significant figures. So that means I can keep my answers to 3 significant figures or to 2 significant figures. So the answer that I get is 151.27 kg, but the final answer that I'm going to accept is 151. I mean, I also could have, kept my answer in 2 significant figures, but then I would be getting exact 150, and that would not match with my statement. Then I'm going to get exact value of 150. The answer should be about 150, not exactly. That's why I will choose to keep my answer in 3 significant figures, which is 151 kg. So m over here is 151 kg. Is this clear? Any problems so far from this A part 1?
No, teacher.
No.
Okay, then if you move state one assumption you made in your calculation, what is the assumption for momentum? This is a
No external forces
Um,
act.
Means it's a closed system.
yeah, you can say it's a closed system, but closed system doesn't mean that, we're talking about the forces, right? I mean, yes, in a closed system, we think that energy is not lost to the surrounding, right? But over here for your collisions, I exactly do not know if the energy is conserved or not. In collisions, energy could not be also conserved. Okay, that's not a problem. Every collision doesn't have to have elastic collision. This could be an elastic collision. That will not modify my momentum calculations. But your external forces like air resistance friction, they would modify your value for the momentum, right? So that's why the assumption over here is they're only giving you 1 mark again. So assumption is no external forces acts on the system during the collision. This should be your statement. During collision. Okay, then after this, now they're saying that the collision lasted for this much. Calculate the average horizontal force on Q during this collision. On Q means what? Q was initially at rest, so initial velocity of Q was 0. And obviously after P strikes with Q, Q starts to move to the right. That means obviously the force must have acted on Q in this direction, right? And after that, the velocity increases to like 1.57 meters per second. This was the final velocity, by the way. Mass of Q was also calculated, 151.27, right? Now, the collision lasted for this much time. Calculate the average horizontal force. If this time is given, wait, are they using... Yes, over here, I mean, the actual second, I mean, we cannot use impulse. I mean, for those of you who have M1 again, most of you guys will continue to continue to use impulse over here, but we cannot use impulse because impulse is not a part of your unit 1 physics, by the way. I should write this down. Do not use impulse. I have to use a derivation here, okay? And the derivation is that I can understand there is some changing velocity happening, right? Change in velocity, I mean, I can write down F equals to MA. I can consider F A is change in velocity over time. So these are the information that I'm using here, right? So if I want to find out the force, I am going to break down acceleration in terms of velocity over time. And mass was 151.27 multiplied with, what was the value? 1.57 minus 0 divided by time was 1.35 seconds, right? If you use impulse here, there is a chance that they might not give you a mark because impulse is not a part of your syllabus. So I'm not going to explain the impulse calculation here again. So you get roughly 175.92 meters per second. So we can write this as 176 Newton, right? This is 176 Newton. Is there any problem from this calculation? 17, I think it's A part 3.
No.
Not easy.
Explain
No,
why.
miss.
Okay, then moving on to part B. Explain why P decelerates during the collision. Your answer should make a reference to Newton's laws of motion. You have to understand that during the collision, when P actually, I mean, obviously Q was not moving at all, right? So P is not responsible for the collision. But when P actually goes towards Q and hits Q with a force of how much? 176 Newton, right? Obviously, Q is not going to just sit there and accept it. According to Newton's third law, Q will also exert a 170 Newton force on P, but in the opposite direction, right? So you have to understand that originally P was moving to the right hand side, and now there's a force acting to the left hand side. So this force, which is by the way the only force acting on particle Q now, because over here we're talking about momentum. In momentum, no external forces is taken part of your calculation, right? So P was originally moving to the right, and all of a sudden the only force acting on Q, acting on P, is to the left. That means this is the resultant force, but problem is the resultant force is going to be a resistive force also, because originally P was moving with 2.1 meters per second to the right, and now a force, only force that is acting on P, is acting towards against its motion. So this resultant force acts as a resistive force, right? And again, if this resultant force acts as a resistive force, for resistive force, if you get the value of your force is negative, you're always going to get the value of your A as negative, because mass can never be negative, right? According to RF equals to ma, mass is a scalar quantity. If this is negative, acceleration is negative. And whenever acceleration is negative, object will decelerate during the collision. Is this clear?
Yes, teacher.
Yes.
Just 1 minute. Okay. Then after this, now if you write it over here that, like, what are the forces acting and everything, then we can say that during the collision, P exerts a force on Q, and according to Newton's third law, Q also exerts a force on P to the left hand side. Acts in the opposite direction to the motion of P. This force acts in the opposite motion of P. So according to Newton's second law, so according to Newton's second law, according to Newton's second law, RF is negative, acceleration is negative, or particle decelerates. So according to Newton's second law, negative deceleration. Right. So this should be your answer. Any problem from this question 17D?
No, match.
No, ma'am.
So we are
Not
actually done with the question 17. So right, this is the end of the question 17 entirely. After this, if we move on to this question 18, it says this is, I think, about what projectile motion stuff, right? Yeah. This is projectile motion. Okay, now it says a golfer hit a golf ball. It was into the air with a speed of this much at an angle of 51 horizontal. I can understand that I have to distribute this horizontally and vertically, right? This is your 52 cos 41 and then again 52 sine 41. Yeah, this is it. The ball landed on the ground near a hole. The ground was 11 meter higher on the starting point of the ball. Okay, and show that the vertical component of the ball's initial velocity is this. This is just what? 52 sine 45 they're asking you. So it's just VH is just 52 sine 41 that you have to calculate using the calculator. Nothing else. Make sure your calculator is in degree mode, not into radian mode. So you get 52 sine 41 and that leaves you with 34, right? Obviously, I can accept 34 because they're saying that my answer should be like approximately 30. 34 is close to 30. So we can accept 34 point 1 or 34 meters per second. Okay, then after this, it says that show that the time taken by the ball to reach the ground was 7 seconds. You should obviously ignore the effects of air resistance. If I draw a very simple diagram of this entire journey, this is how the diagram looks. Over here, the object actually travels 11 meters above the ground. Okay, that's why the object will actually hit this hole on 11 meters above the ground, right? So this is actually the distance traveled. This is the maximum point of the ball where it eventually comes to zero. If you focus on the vertical component entirely, you can understand that object traveled s of 11 meters up plane in the upward direction. The displacement s is positive. In the upward direction, object was decelerating because it started with a velocity of 52 sine 41. Whatever that value is, it had a velocity there, right? But along the journey, velocity decreased to zero. So obviously acceleration was negative. Object was decelerating. So if you focus on vertical motion, so you get the answer for your time, right? We have initial velocity, final velocity, and acceleration and distance. Everything we need to calculate the value of your time, you can use that. So let's use the easiest equation. T equals to 0 minus 52 sine 41 divided by 9.81, right? I'm using the equation V is equals to U plus 80, right? The easiest equation that is ever in entire equations of motion. From there, I just make T the subject of the equation. So you have 52 sine 41 divided by 9.81. That leaves you with 3 point, wait 1 minute. For the ball to reach the ground. Okay. Problem is that, I actually am not sure over here if this is 1 minute. Near the ground, 11 meter. Yeah, over here, this is one of the possibilities of the pathway. The other possibilities of the pathway could be like this also, right? So problem is that if you are considering that, the final velocity is zero at this point, this could not be also a correct answer. So I'm not sure exactly which of the pathway was followed here. So it's better to use the displacement over here, because doesn't matter whatever the pathway you use, the displacement is always 11. This is a easier, more more safe way to use, because if I'm using this idea that object eventually hits the entire wall over there at 11 meters, which is 11 meters above the ground, then over here it could not also be the possible answer. So that's why if you use the total scenario, that whatever the pathway followed, that total displacement traveled is 11 meter. If that's the case, and we're not aware what is the final velocity and everything, if that's the case, and I'm using the equation s equals to ut plus half at square, then you have u as 11, so s as 11. This is going to be 52 sine 41t and 41t, and then this is what? This is going to be negative 4.905, right? Half multiplied with 9.1 leaves you with 4.905 t square. Rearrange the equation. Obviously, I can understand that no need to do factorization. I can just directly use my calculator to get the value of my 4.905 minus 52 sine 41 and 11. That leaves you with 6.62 second. The other time that you get is 0.34 second, right? So these are the two values that you get. Now in this case, over here you should find out the time taken by this situation, right? Exactly why are you getting two values? This is your hint that this is not the correct answer, because if it was the correct answer, then I was supposed to get only one value. And again, why am I getting two values over here? I'll explain. Because exactly at 11 meters above the ground, it was 2 times 11 meters above the ground, right? When it was exactly over here at this point, which was maybe after 0.34 seconds from the release, and then again at the final stage when the time was 6.62 seconds, right? So basically we're going to accept this value, right? The total journey, the time of flight for this journey is 6.62 seconds, not this one, where obviously at this point also it was 11 meters above the ground, but not a part of my calculation. So not going to accept this one, only going to accept this one. Is this clear? Any problem from part B?
No, teacher.
Okay, then if we move on to your next part. Now I think they're talking about range or something, right? The hole is a horizontal distance 250 meters from the starting point of the ball. Deduce whether the ball landed within 5 meters of the hole, and your answer should ignore the effects of air resistance. Like I have to say that if the ball will fall within the 5-meter range over here or not. So for that, I basically have to find out the range in this case. So for your range, I already have the time, right? That was 6.62. So for your horizontal motion, if I focus on, I understand that for horizontal motion, what is the case? Object always moves with constant velocity. The only equation I can use for the horizontal section of the part is V is equals to ST, right? So S equals to VT. So if that's the case, then it will be 52 cos 41 multiplied with your time, 6.62 seconds. And if we calculate it now, that 52 cos 41 multiplied with 6.62, you get 259.8, which is approximately 260, right? Just one minute, please. Sorry guys, actually I had to receive a call. As I was saying, there you get 259.8 meter. Approximately, we can write this as 260 meter, right? So it was already saying that if this is like within the range of 5 meters from the hole or not. You have to understand, if this total is 250, if I create a circle with a range of 5 meters, that means the maximum range that I can get, right? This is your maximum range, right? This should be like 255, or the minimum distance in order to be 5 meters from the hole from that hole is going to be 245, right? So my range was supposed to be within this range, 245 to 255. Problem is I got approximately 260. So we have to write that 260 is greater than the what is this, upper bound or upper limit of your range. So it is not 5 meters from the hole, right? That should be your answer over here, the last statement, that the range was supposed to be 255 meter. Right? Just writing this is enough. So this is the end for your question 18C. Any problem from question 18 entirely?
No.
No, teacher.
No.
If there is no problem from question 18, then we'll quickly move on to question 19. There, they're talking about a falling sphere. Viscometer is a device used to determine the viscosity of a liquid. A sphere falls through a cylinder containing a liquid. The terminal velocity of the sphere is measured. Explain why the temperature of the liquid should not increase during this measurement. Because this is supposed to be a controlled variable. Because the main thing that we're trying to calculate is viscosity, and viscosity depends on temperature, right? Or kind of is inversely related to temperature. So if the temperature increases, viscosity would decrease, and it would be very difficult for us to calculate a very small value of the viscosity, right? The smaller the data, the larger the uncertainties. That's why it's very difficult to calculate smaller viscosities. As they're only giving you 1 mark, no need to write all of these things. Okay, you can just write, viscosity would decrease with increase in temperature. That's enough. With increase in temperature, right? Okay. Then after this, they're saying the scientists measured the terminal velocity of an aluminium sphere as it fell through glycerol. Show that the weight of the sphere is about this much. Density, diameter. I want to find out the weight, right? Obviously, if this is a terminal velocity, what happens? Weight is equals to upthrust, right? All the forces are equal. So if weight, not exactly weight is equals to upthrust, weight is equals to upthrust plus drag, right? This is how the weight the diagram is supposed to be. Upthrust and drag, that is equals to weight, since all the forces are balanced. So we can say that, the combination of drag and upthrust is equals to weight. Okay, then we have to find out the upthrust, right? Show that the weight is this much. Using rho, g, and diameter, using this diameter, I can find out the upthrust. For drag, aluminium sphere as it fell, I want to find out, we have to show this weight, but 1 minute. The problem is that in this case, we cannot have any idea about drag, right? We do not have any idea about drag. Without drag, no, in this case, I cannot use this equation because over here, if I want to use this orientation, the value for your drag is missing. So I cannot, if I calculate drag again without the value for your viscosity, right? Because the formula for drag was 6 pi r eta v term. We have to find out the value for viscosity, then terminal velocity, then only I can calculate the value for your drag. So okay, I cannot use this one, but I can consider in this way that, I have the volume. Using the volume and gravitational field strength, I can calculate the mass. And using this mass, and again, using volume and density, I can calculate mass, right? So using the equation m, rho v, and from there, rho is what? Density of the aluminium is 2.7 into 10 to the power 3. Whatever the diameter of sphere is, that was the volume, that will give you the volume of the sphere again. So volume of the sphere is 4 by 3 pi 7 into 10 power minus 3 divided by 2, everything under a cube. This will restore the value for your mass. Okay, so you get 2.7 10 to the power of 3, multiplying this with 4 by 3. 1 minute. Then 7 into 10 to the power of minus 3 divided by 2 power 3. So from there you get 1.54 into, sorry, I forgot to multiply pi here. Now, so you get 4.85 into 10 power minus 4 kg. But if this is the mass, then in order to calculate weight, it's just going to be mg, right? So you just have to multiply 85 10 power 4 with 9.81. So you get 9.81. And from there, you can write 4.76. Right, so this is the weight. This is approximately 4.8, so we can accept 4.76 as your final answer. Is this clear? Any questions about why we cannot use this equation in this case?
No.
Yes, ma'am.
Okay, then if we move on to your next part, there they're asking the terminal velocity of the speed is this. Deduce whether it follows the Stokes law or not. Density of glycerol, viscosity of glycerol is now given. Okay. I know that from there now I can calculate my upthrust, right? If it wants to follow the Stokes law, in that case, your combination of all the forces should be balanced and everything. So you have to calculate upthrust and then drag and then every value. So we already have the value for your weight. If we calculate the value for your drag, which is going to be 6 pi r eta v term. So for your 6 pi, that's a constant value. R is 7 into 10 to the power of minus 3 divided by 2. From the previous part, we got it. Eta is given. Viscosity 9.5, 10 to the power of minus 1. And V term is also given 4.05, 10 to the power of minus 2. So if you calculate all these values, 6 pi, then 7 into 10 to the power of minus 10 power minus 3 divided by 2, then 9.5 into 10 to the power of minus 1, and then again 4.05, 10 to the power of minus 2. So you get 2.54 into 10 to the power of minus 3. So this is 2.54, 10 power minus 3. Then again, your upthrust is just what? Rho GV, right? So for your rho GV, rho is density of the glycerol, positive 3 it should be. And then again, multiplied with G is just 10, right? And volume is not given, but I have to calculate the volume again separately, right? So not 10, 9.81. It's going to be 4 by 3 pi, and then 7 into 10 power minus 3 by 2 power 3. If we calculate all these things, 1.26, 10 power 3, 9.81, and 4 by 3, then pi, then 7 into 10, 1 minute, 7 into 10 power 3 divided by 2 power 3, that leaves you with 2.22, 10 power 15 actually, sorry, midterm. No, 10 power 3, sorry. So you get 2.22 into 10 power minus 3 here. And this is also in newtons. This is in newtons. And weight I already know, right? So in this case, if the drag is this much, if you want to find out, if it follows your Stokes law, in Stokes law, what was the case? Drag was supposed to be weight minus upthrust, right? If drag weight, we got that as 4.76 into 10 to the power of minus 3. You have to subtract this with 2.22 into 10 to the power of minus 3. I'm going to get 4.76, 2.22, that's 2.54 exactly, right? As you can see. From there, this value, according to your calculation, doesn't matter whatever process you use, the value for your upthrust is same. So you have to say that, yes, the conclusion is consistent, or this calculation is consistent, or students' values from the calculation is consistent with the Stokes law. So this does obey the Stokes law. Is this clear?
Yes, teacher.
Yes, miss.
Can you repeat how you
Yes.
are concluding that it obeys Stokes law?
How it obeys Stokes law. If it was not obeying Stokes law, Then over here, I mean, this is the equation in Stokes' law we use, right? Resultant force is 0, so weight is equals to upthrust plus drag. That means from this equation, if I rearrange it, drag becomes weight minus upthrust, right? So this is the equation for your Stokes' law. From this equation, the value for the drag that you got, and again from the 6 pi r eta v term for the value of the drag that you got, they're exactly similar. If they are similar, then obviously they would obey the Stokes' law.
Oh, okay. So that means drag is equals to V minus U, right? So W minus
Drag W minus U, according to your Stokes' law. And this is the drag equation that you calculate. So this is actually equation that you can calculate from the equilibrium forces, right? And this is the formula that you got for your Stokes' law. Equilibrium force also and Stokes' law also gives you the same magnitude. That means obviously it obeys the Stokes' law. Stokes' law. State one condition that must be made for Stokes' law. What is the answer, guys?
it should be in laminar flow.
Laminar flow and
The sphere should be small and move slowly.
slowly, right? So should be in laminar flow. Slow speed. Okay, then this is it. After this, if you move on to your part C, a scientist used the viscosity to measure the viscosity of blood. The viscosity of blood is typically within the range of 3 to 4, and explain why the scientist should use an aluminum sphere with a much smaller diameter than the sphere used in glycerol. Do not include calculations in your answer. Viscosity of glycerol was this much. You have to compare this time, right? Understand that viscosity of glycerol was 9.5, whereas the viscosity of blood is like half of that, right? 3 and 4, within the range of 3 and 4. So obviously this is quite half of the viscosity of the, what was that, glycerol. Another thing, in this case, if the value of your viscosity of blood is very low, is depending on viscosity, what force was acting? Drag was acting, right? Drag was 6 pi r eta v term. Over here they're saying that the scientist should use a aluminum sphere with a smaller diameter, like a much more smaller diameter should be used here, because understand that in this case the most difficult thing to calculate is your radius. So is your actually terminal velocity, right? Because if the ball actually falls with a very large speed within blood, then obviously that will be very difficult for us to measure the speed. So we have to make sure that somehow your velocity is very small, so that it can be easily measured. So over here, from this case, what we can understand that if the value of your viscosity is dropping down, drag will drop down, and we can also rearrange this equation and write it like this: that v term is 6 pi r, so it is actually force divided by 6 pi r eta, right? In this case, if the value for your viscosity is dropping down, radius will also, radius is actually an internal factor for the sphere, sorry. So viscosity drops down, velocity will also drop down. So if I'm getting very small, made a mistake, velocity will increase, right? Because they're inversely proportional. So if I'm getting a very large velocity inside a fluid is very difficult to calculate, or very difficult to measure. That's why I have to make sure that my terminal velocity is not that much very large. The terminal velocity should be small so that I can easily measure this. So that's why in order to keep your velocity same, I have to decrease your decrease your radius also. For a smaller radius, it should be directly related to your velocity. So for a smaller radius, a smaller velocity can be calculated, and then we can easily find out your terminal velocity, right? Or this will lower the terminal velocity. And for that, at a lower terminal velocity, laminar flow obviously can be maintained, right? So for all these cases, a smaller radius should be used. A same sphere we can use, same aluminum sphere we can use, but we have to use a smaller radius. Is this clear?
Yes, teacher.
So we can say that viscosity of blood is lower than glycerol, So for a smaller viscosity, drag force decreases, and for smaller viscosity, your terminal velocity also increases, which could be too large to obey Stokes' law. So in order to reduce, or in order to make your object, make the sphere move at a lower terminal velocity in laminar flow, the radius should be small. If the small because for a smaller radius, the value of your terminal velocity will also decrease. Any questions?
Miss, how does the radius decrease the terminal velocity? I'm
How will
sorry,
the
yeah, how does it increase it? Doesn't the equation show that if you decrease it, it will increase?
oh wait, sorry. If no, over here, are you talking about radius or viscosity,
Radius,
velocity?
radius and
Radius.
velocity.
Yeah, no, actually, if they're actually inversely proportional, decrease in radius will increase the velocity. But we can at least talk about this one. Decrease in viscosity. A decrease in viscosity will increase the velocity. But from this equation, we cannot conclude that then. 1 minute. I can consider using the equation. I can now use the equation like, 6 pi r eta V term is equals to weight minus upthrust, right? Upthrust is actually a constant value because volume displaced by the water density and what was that? Gravitational field strength, that is constant, right? It cannot change. So in this case, if you think that over here, in order to maintain this, right, if radius decreases, right, in that case, weight on the other side, what will happen to weight? Weight on the other side would also have to decrease, right? Reducing the value for your radius reduces the value for your weight. If you're using a smaller weight, that means again the total value for your, but then again, yeah, if the value for your weight decreases, you have to understand that in this case, weight is also related to mg. M is actually what? M is actually volume, G, yeah, volume, G, and density and upthrust, right? If you're using smaller radius means, you have to think about it in this way. Over here, for a volume of the weight, if you're using smaller radius, the entire weight over here decreases. If weight decreases, drag in this case also must decrease. If drag decreases, velocity must decrease. This is how they're referring to. Yes, that's why we have to use a smaller radius. Smaller radius gives you smaller volume gives you smaller mass gives you smaller weight. Smaller weight means that now the drag over here decreases. If drag decreases, terminal velocity, the value for the terminal velocity will be much lower to fit in the Stokes' law theory. Is this clear now, Carl?
Yes, miss. Thank you.
And for everyone else also. Previously, I was connecting r with v over here, but they are inversely proportional. For smaller r, velocity must increase, right? So that was not a correct explanation. This is how we're supposed to connect it. I will obviously have to use this information that for smaller viscosity, velocity will be too large to fit in for the, what was that, Stokes' law. So velocity must decrease. In order to use that idea, we're again going to use this equation. Any question from this explanation?
No, teacher.
No, teacher.
No, miss.
Okay, so if I just take this to the very bottom, I'm going to leave it right there. And after this, if we start. For viscosity of blood, is lower than glycerol. To obey Hooke's law,
Isn't it Stokes' law?
oh sorry, yeah, Stokes' law, sorry. Stokes' law, then reducing R reduces weight, Yeah, we can just directly connect this to weight. Okay, reducing R reduces weight from the equation rho Vg. Drag also decreases as upthrust is constant for smaller weight. Drag also decreases.
Miss,
1 minute, please. Drag also decreases the velocity. Yes, Tanisha, you can see.
are drag and upthrust acting in the same direction?
Yes. Drag also decreases, decreasing the velocity. Yeah, this is enough, right, to maintain the lower laminar flow also. That's not actually needed. Over here, this was the main case, decreasing the velocity to fit under the Stokes law. So this is enough. Writing about this much is enough is for your 5 marks. Is there any problem from this part?
Miss, don't you have to do any calculations?
No, it says in the question that do not include any calculations. We just have to explain.
Yeah, is this enough for 5 marks? So,
Yeah, we're talking about that, the difference for the density of blood lower. Then you're saying that if the density is lower, then you get the viscous velocity to be very large, right? You can also refer to the equation here, that how does your decrease in viscosity decreases the velocity. You can write down the equation here as V equals to F6 pi R eta. Okay. After this, they're talking about reducing R reduces weight. And after this, in that case, what? As upthrust is constant, decreasing drag decreases velocity to fit in the Stokes law. This is enough for 5 marks.
Shouldn't you say that it's easier to measure if the velocity is lower?
It's easier to measure when the velocity is lower. No, it's not easier to measure if the velocity is lower. I mean, if the magnitude of the terminal velocity is lower, right? Yeah, you can say that, no problem. You can add this, but that's not mostly related to your question over here, because in this case the velocity must fit in Stokes law. It should not be it's easier for you to measure the value of your velocity, but you can say that that's not a problem. You can connect it over here, that decreasing the velocity, which maintains laminar flow also, by the way, right? At low speed the laminar velocity can be maintained, right? Or laminar flow can be maintained, which maintains laminar flow and can be easily calculated. But I'm not sure if for the last 2 points you're going to get any marks or not, but they are connected to this answer. You can add them, no problem. Okay, is there any problem from this question 19?
no, teacher.
No.
Then just 1 minute. I'll stop the recording and then